Now that we spent quite some time talking about what digesters are, how they operate, which parameters you have to be careful about, it's finally time to talk really about how we do it. Let's bring anaerobic digestion to practice. Now that practice can be extremely diverse. You have large sludge digesters which have an egg shape and which you may have seen driving past the highway. There's more cylindrical reactors that you'll find, like the Dranko system that you see here, a dry anaerobic composting. And then there's very small scale ones, of which there are actually millions worldwide, that locally convert small amounts of household waste into a usable biogas. So what's going to drive the design of our reactor? Of course, a first step is the wastewater or the bio-waste. You can imagine brewery wastewater, very liquid, only a few grams per liter of organics, is very different than the organic fraction of municipal solid waste, and that's very different from manure again. Then you need to think about your local conditions. What's the temperature? Am I in the tropics or am I in Norway? And what's the available surface area? Do I have a large block of land available to install my system, or am I in a city and I need a very compact solution? Compact solutions are more expensive, but it's doable to save a lot of land. What are my local requirements? What is my government tells me that the water quality has to be that comes out, and am I obliged to protect the receiving environment against possible pathogens? It's a very important aspect. And it's all about money. How much money do I have to build this system? The more money you have, the more you can do to really even fully recover all the water that came into the anaerobic digester, and if you want, you can even produce drinking water from it. So next to these design decisions, you have a few things that you can also change. There's knobs you can turn. You can change the hydraulic residence time, how long does the water spent in the reactor, and I could uncouple that and change my sludge residence time. How long is the biomass really producing the methane staying in the reactor? How high is the loading rate, which is a mixture of hydraulic residence time and concentration? And do I add some co-substrate to really fine-tune the composition of what comes into my system? Very important to consider also is methane solubility. This is a bit of a sidestep, but it's very important to note. In a reactor where I produce methane, part of the methane stays in solution. Actually, at saturation, 20 degrees Celsius, you can dissolve some 28 milligrams of methane per liter. And remember, a kilogram of methane corresponds to about 25 kilograms of CO2 greenhouse gas equivalents. So you have to be careful that not too much methane stays in solution for either accidental release afterwards and have this high carbon footprint, but also I recover less energy, right? Because all the methane that stays in the water is not biogas that I have harvested. Now, how can we deal with this at the reactor level? There's a few things. The stronger the wastewater coming in, the lower the impact of the residual methane is. What does that mean? Well, if I have something like, let's say, domestic wastewater with 0.5 gram of organics per liter, and I put it in a digester, and I have 25 milligrams of methane staying in solution at an impact of some 25 times CO2, you see that the impact of the methane coming out is at the level of 0.5 gram per liter of greenhouse gases. So for a diluted wastewater, if a lot of methane stays in solution, I have a high impact. Of course, if I have grams and grams per liter of organic matter, that little bit of methane, that amount of methane then actually becomes a very little bit in comparison. So the stronger the wastewater coming in, the less of an issue it is. Gases also have lower solubility at high temperature, so if I work thermophilic, less methane is staying behind, and that's also better. I can also technically intervene, and on the effluent coming from the digester, I can put a degassing unit and really pull out the methane, so I have low emissions. Next, once I know feedstock and how I have to operate and how strong it is, I can choose to do my process in one step or two steps. A single stage process, of course, it's simple. I need one reactor, and it's a one-pot reaction. Everything happens in there. But I need to do the hydrolysis and the fermentation and the methanogenesis all in one go, so I need a longer residence time. And it's more difficult to steer because I need to have different processes going on at the same time. So the alternative is a two-stage process, in which I say I first have a shorter, quite intensive process, in which I aim at hydrolyzing and fermenting. So I can work at a somewhat lower pH, high temperature typically. And then I generate a stream containing these fatty acids, and that goes in the second reactor where I produce the methane. So this is dominated, and the second one by the methanogens. And by doing that, I can, of course, for the two different processes, optimize the conditions. But I need more control, and I need to build two reactors. Again, it's a choice. Is there necessarily in the reactors or in the engineering a best choice? To my opinion, not. It's very location dependent, and it's also dependent on who sells you the reactor and the system and the local expertise available. So when we now talk about reactors, we're not going to talk about some specific best solution. There is a solution. Now the simplest solution, maybe this first one that I discuss may not be the best solution. It is typically not a good solution, but it is the cheapest solution, is the anaerobic lagoon. And so an anaerobic lagoon is applied in many cases in developing countries. It's very cheap because it's just a pond in which you put a liner. The water goes through, depth is 2 to 5 meters. You can only do a low organic loading rate because it's not well mixed, and the water typically stays in there up to about 5 days. So this is just a way of treating wastewater coming out of a process. Let's say palm oil mills, their wastewater you can treat this way. The problem is, of course, is that the methane that is generated in this process is just gassing out into the atmosphere. And you don't really treat the water very well. So I'd say it's reasonably robust, it's very cheap, it's possible if you have a lot of land area, but of course it leads to a large emission. A solution to that now is the so-called covered anaerobic lagoon, where on the top of this pond you also put a plastic liner and you close off the whole system as if it were a big plastic bag, and then you can still collect the methane and do something with it. But it's let's say a low performance first stage solution for wastewater. We need to move a step further, and so we need to rather build reactors for anaerobic digestion. And unfortunately, this comes with a lot of acronyms. So the simplest reactor we'll discuss first, mainly for slurries, things like manure, is the continuous stirred tank reactor. And then we'll discuss different options in which we manage to separate the liquid from the solid, so to keep the sludge in the reactor while the water or the feedstock goes through. There's the so-called UASB, there's the EGSB, the IC, and the ANMBR, and I'll explain those acronyms later. As a third option, you can also immobilize the biomass, so put the biomass on a carrier, and then you have, for example, an anaerobic filter or a fluidized bed system. We will not discuss the third options in this course. The simplest reactor design for anaerobic digestion is the so-called CSTR, the continuous stirred tank reactor. It's nothing more than a simple reactor in which we bring our influent or wastewater, and it comes into a large tank that is typically stirred. This is just for illustration. Typically the stirrers can be on the side and they're put there in a way that you have an adequate mixing of the reactor. These type of reactors are very suitable for sludges, anything that is quite viscous. The gas that is being produced is moving nicely to the top and is collected there. Sometimes in the top of this reactor a netting is put and a little bit of oxygen is injected. And this allows to oxidize sulfide in the biogas to elemental sulfur. And you form a biomass of sulfur oxidizers there that often falls down into the reactor. And so this is a first quite robust way of treating the biogas. As you can see, the CSTR, it's a quite simple design, right? It's just a tank with a stirring. Of course, stirring is also an art if you have a reactor of 2000 cubic meter size. So there's some thinking on how to stir that system, but in general, it's quite simple. The mixing, make sure you mix enough. If it's too high, you're really gonna cause a lot of shear, you're gonna make foam, and it costs you a lot of energy. If you don't mix enough, everything is unevenly distributed, and I will not have good methanogenesis in this reactor either. They have moderate loading rates because they're not super well mixed and controlled. So let's say you can feed about on average 5 kilograms of COD, of organics, per cubic meter of reactor per day. And the residence time, depending on how concentrated the material is, equals the sludge residence time, equals the hydraulic residence time. It's a continuous stirred tank reactor. It's typically more than 20 days, up to even 150 days in some cases. So we use it for streams that have quite high solids content, sludge, manure, municipal solid waste, energy crops. We do it because it's simple and it's good for slurries, but we wouldn't do it for a low loading, so we need a big reactor. And the effluent quality isn't really good because we mix the waste with everything together, and so what comes out of the reactor is what is in the reactor. Right? So you still have to settle and separate and deal with a quite dirty effluent. This is what they look like. Nothing spectacular. It's just a cylindrical tank. An interesting next example is the upflow anaerobic sludge blanket reactor. The second type of reactor I will discuss is the upflow anaerobic sludge blanket reactor, the UASB. UASB was developed in the 70s, and rather than, as the CSTR, mixing the whole reactor, here we bring in our wastewater in the bottom of a reactor and we make it go up in an upflow of about 1 meter per hour typically. Because the water goes up and gas is being formed, we get the formation of dense aggregates of biomass called granules. And so these granules are very dense assemblies of microorganisms that form your methane. And because they're so dense, rather than flocks which float, these dense granules, they stay inside the reactor, so they phase separate. You get a sludge blanket. On the top of the reactor, we introduce a so-called phase separator. And in that phase separator, the gas is collected and leaves from the top here. So we separate the gas there from the liquid. And because the solids stay down in the reactor, we have an effluent which is mostly solids free, and we get a better quality of our effluent. So as you can see, the upflow anaerobic sludge blanket reactor has a biomass that stays inside the reactor while the water is flowing through. And this is because under these conditions, microorganisms aggregate in what we call granules. And granules is like caviar in wastewater treatment, small spherical black balls that contain methanogens, that contain your hydrolytic organisms, and that contain your fermenters. And because they're dense balls, they tend to sink quite and settle quite quickly. So I can send the water through at about, let's say, 1 meter per hour. The wastewater goes up in the UASB, and the granules, they just stay suspended, they don't come out. And so you can see as an advantage, I'll have a better effluent quality because the solids stay behind in the reactor, it doesn't come out. So this was the big advantage when the UASB was developed for a lot of wastewater, is I get better effluent quality. And because I have a meter per hour upflow, there's some better mixing. The methane that is created in the reactor also causes mixing. So I can have a higher volumetric and organic loading rate, 10 to 20 kilogram of organics per cubic meter a day. Disadvantage? Well, of course, if I have a slurry like manure, I cannot use it on a USB. And I can typically use it for low to medium strength wastewaters. There's aspects like if you have high salinity, you need to be more careful. There's solutions nowadays to deal with quite a high salinity, but it's still sensitive. And you can have scaling. As I mentioned, the pH is quite high in a methanogenic reactor. And if I have, for example, a pulp and paper wastewater coming in containing quite a lot of calcium, the calcium will precipitate as a calcium carbonate inside the reactor. And that's a problem. I can have installations with several tons a day of calcium carbonate lost, which means that the reactor has to be stopped and you have to get all of that material out. So they are very successful worldwide in breweries and in the dairy industry.